What if I told you NASA just pulled off one of the hardest magic tricks in science, spotting a tiny, cold alien world hiding right next to a blinding star, using a telescope that cost about $10 billion to build? Because stars don't just outshine their planets, they erase them. Imagine trying to see a firefly hovering beside a stadium spotlight, then doing it from dozens or hundreds of light years away. And yet, with the James Webb Space Telescope, astronomers just reported compelling evidence for a planet about Saturn's mass inside a dusty ring system around the young star TWA7, a planet candidate called TWA7b. But that's not the strangest part. The strangest part is how Webb did it, and why this method is basically a sneak preview of the future moment everyone wants. A direct look at a smaller, colder world that could someday resemble Earth. So here's the mission. How do you see an alien world when a star is trying to delete it from the picture? First, quick context, because seeing alien worlds can mean two different things. Most exoplanets are found indirectly, like noticing a planet by how it tugs on its star or dims it during a transit. Webb can do that too, and it's extremely good at it. But the title you clicked suggests something rarer: direct imaging, actually capturing the planet's light in an image, not just its shadow. And Webb is built for the one advantage planets still have over stars. In infrared, planets glow with heat, and dust rings shine too, if you can block the star's glare. That's the battleground. A star is basically a cosmic flashlight aimed at your telescope. Even in space, light scatters inside optics and creates patterns and glare. That glare forms a bright halo that can bury anything faint nearby, like a planet, under noise and diffraction. So, astronomers don't just need a powerful telescope. They need a way to turn a star off, or at least turn it down so hard that the planet can finally show up. That's where the trick begins. Webb carries specialized tools called coronagraphs, tiny masks and optics that block a star's light so faint objects nearby can be revealed. Two of Webb's instruments, NIRCam and MIRI, have coronagraphic modes designed for this kind of high-contrast work. But a coronagraph alone doesn't give you a perfect black circle where the star used to be. Even after blocking the star, there's still leftover glare, like fog around a street lamp. So astronomers pile on this second part of the trick: advanced image processing that models the remaining starlight and subtracts it away. And this is where the story flips. Because in the TWA7 result, the team used MIRI's coronagraph to suppress the star, then subtracted the residual starlight, revealing a faint infrared source right where a planet should be if it's sculpting the dust rings. But can a faint dot really be a planet? Here's what NASA release says in plain language. Astronomers found a faint infrared source in the debris disk around TWA7. It sits about 50 times the Earth-Sun distance from the star, right in a gap in one of the disk's rings. The team says they ruled out a moving solar system object that just happened to be in the same patch of sky. They also note a very small chance it could be a background galaxy. But overall, the evidence strongly favors a planet. They estimate it could be a young, cold planet around 0.3 Jupiter masses, roughly Saturn mass, and the system is young, around 6.4 million years old, and about 111 light-years away. If confirmed, it would be Webb's first direct image discovery of a planet, and the lightest planet seen with this technique outside our solar system. But that's not the only time Webb has seen worlds directly. Back on September 1st, 2022, NASA announced Webb's first ever direct image of an exoplanet, HIP 65426b, captured using Webb's coronagraphs. That moment mattered because it proved something critical. The coronagraphs weren't just theoretical, they actually worked in space, suppressing starlight enough to isolate a planet's glow. And then, Webb went even closer to home. In July 2024, Webb directly imaged Epsilon Indi AB, a giant planet roughly 12 light-years away, one of the coldest exoplanets ever directly imaged, again using MIRI's coronagraph. So the TWA7 candidate isn't a one-off miracle. It's part of a pattern. Webb is steadily pushing direct imaging toward cooler and lower-mass planets. But micro cliffhanger, direct images are only half the story, because the real alien world reveal isn't often a picture, it's a chemical fingerprint. Webb can also see alien worlds by analyzing how starlight filters through a planet's atmosphere during a transit. In August 2022, NASA reported Webb's first clear detection of carbon dioxide in an exoplanet on WASP 39b, about 700 light-years away, using Webb's NIR-SPEC instrument. That matters because carbon dioxide is a powerful tracer for understanding atmospheric chemistry and, in some cases, clues about formation history. And Webb's result also showed the precision needed to hunt for molecules in thinner atmospheres in the future. And this gets wild fast. Follow-up peer-reviewed work with Webb have reported additional chemistry in WASP 39b's spectrum, including sulfur dioxide features in the mid-infrared with MIRI. So Webb isn't just snapping postcards. It's running remote chemistry on worlds that are literally not reachable. But the next question is obvious. Can Webb do anything like this for rocky planets? Rocky planets are smaller, dimmer, and their atmospheres can be thin or gone. That's why you'll often hear careful language like hints and constraints instead of confirmed breathable air. That caution is not a weakness, it's the science working properly. For example, NASA notes that early Webb work on TRAPPIST-1b found little evidence of an atmosphere in that case. And even when Webb detects something intriguing on a rocky world, scientists often frame it as narrowing possibilities, not declaring certainty. Which brings us to another recent twist. On December 11, 2025, NASA reported Webb measurements suggesting the ultra-hot super-Earth, TOI 561b, may be surrounded by a volatile-rich, thick atmosphere based on an emission spectrum compared to models. This is a planet so hot it's described as a lava world scenario, yet the data suggests it may not be a bare rock. That doesn't mean habitable, it means Webb is pushing into a new regime where even rocky planets can be tested for atmospheric presence, carefully, with models and with uncertainty clearly stated. Now, micro cliffhanger. Here's the part that feels like upgrading the telescope without changing the telescope. There's another technique that's gaining attention because it can extract information at extremely tight angular separations. It's called kernel phase interferometry, a post-processing method that models a telescope like a densely packed interferometer to access separations that standard imaging struggles with. In late 2025, researchers reported a first demonstration of kernel phase interferometry on JWST MIRI, discussing prospects for future planet searches in challenging environments. Translation? Sometimes the path to seeing more worlds isn't only bigger mirrors, it's smarter math applied to the photons you already captured. But, and this matters, these techniques still have limits and they're not a magic key to instant Earth 2.0. So, what comes next? First, for TWA7b, the obvious next step is follow-up observations to verify the source is truly a planet and not a rare background object, and to better pin down its properties. The NASA release explicitly frames it as a candidate and describes ongoing and future observations. Second, watch for Webb results that combine coronagraphy with improved processing to push toward even lower masses and closer-in separations. High-contrast imaging is a defined, evolving technique in the JWST ecosystem, and it tends to improve as teams refine calibrations and algorithms. Third, the next big leap in turning down stars is expected to come from NASA's Nancy Grace Roman Space Telescope, which is planned to demonstrate an advanced coronagraph and is scheduled to launch no later than May 2027, according to NASA. And that's the bigger story. Webb is proving the methods, and Roman is meant to expand the playbook. So, did NASA find a way to see alien worlds with a $10 billion telescope? Yes, but not in the Hollywood sense of instantly zooming in on continents and city lights. What Webb is really doing is more impressive and more honest. It's learning how to erase starlight, isolate planet light, and turn faint signals into physical facts, masses, temperatures, dust rings, and chemistry. The TWA-7b candidate shows Webb can potentially image planets with masses comparable to the giants in our own solar system, embedded in real, structured planetary systems as they form. And the atmosphere work shows that seeing a world can also mean reading its air like a barcode, molecule by molecule, while being transparent about what's confirmed and what's still uncertain. If you want the honest cliffhanger, it's this. We're watching the toolbox for finding truly Earth-like worlds get built in real time, one blocked-out star at a time.